This is my first, oh, is it now working? Okay. I am very happy to be here. This is my first PyCon, and some of you may have seen our tutorial on IPython a few days ago. We were able to get a last-minute slot for a talk, and it's great to see some new faces here. I am going to do a talk in two parts. First, I will do a brief overview of the project, and then a bit of a high-wire act with actual demos, which is obviously what they tell you never to do in a talk, but we'll see. You'll watch me crash and burn. So I am going to tell you a little bit about the IPython project, which is a project that I started years ago, and where now a group of developers have joined me in trying to make the best possible use of the Python language while working interactively. The I in IPython is for interactive, and the motivation for it comes from my own background and the background of several of the other developers. We're scientists, several of us are physicists in the team, and in scientific computing, the kinds of work we do with computers are rarely with a well-defined task in advance. We tend to work with data, we have libraries, we have tools, we plot things, we ask new questions, and rarely do we have a well-defined specification to code against. So having an interactive tools that lets us directly play with the data is extremely important for us. However, exploratory computing is not just for scientists, and I'd like to make the point, could I get the slide back? Thank you. I'd like to make the point here that IPython, even though we do a lot of work for scientific computing, there's nothing inherently scientific about it, and it should be a tool that could make many of you also productive while you work with Python, and get you closer to the language, get you closer to the tools. Python is a great language for interactive work. The language doesn't require you to declare variables. There's very little boilerplate. It has great introspection capabilities. However, the default interactive environment is just a starting point. It's kind of limited. When you're working interactively in a computer, one of the most natural things to want to do is to look at your files. Well, that doesn't work. You have imported something, you'd like to find out about it. The shortest amount of typing doesn't tell you. Obviously, there are ways of seeing your files. There are ways of finding information about objects, but they require too much typing. You try to run a script, and you use the familiar tilde syntax, and that doesn't work. You run a script that has an error, and you get error messages that contain information, but that could certainly be improved. And while working interactively, all these things matter, and we spend hours and hours at the interactive console. So we think we can do better, and over the years we've tried to do better. So in IPython, if you type ls with standard Unix wildcards, you see something that makes kind of sense. If you ask for information about the OS module with OS question mark, IPython, using the machinery that the language provides already, will do its best to tell you everything it can about it. Where is it defined? Where did it come from? What docstrings are in it, etc., etc. If you're curious and you would like to know more about an object, you can type 2 question marks. And IPython will basically do its best to dig deeper when possible. I'm sure this will happen 3 or 4 times. IPython will do its best to dig deeper. The language offers the inspect module, which is designed basically to allow you to drill into its own machinery, and IPython will show you the source code for any object that you want, syntax highlighted, properly formatted, not only at the module level. You can ask for source code from a function. You can even ask for source code for a function you defined interactively. That's something that Python can't do by default. We've played a few tricks to make that possible. So when you run code, 99% of the time you spend your time debugging, not getting results. So when things go wrong, it's important that the error messages that you get are easy to read and informative. This is what a traceback from IPython looks like by default, and you can even ask for IPython to give you values of all of your variables at the point of the exception automatically, so that you quickly find out, understand what's going on. I personally find this far more informative than that. And I hope you'll agree with me that it is. So we have had this for a long time. This is the terminal-based IPython. A quick show of hands, how many of you have used IPython at the terminal? So quite a few of you, and most of you have used this. How many of you have used the new Qt console? Much less. And how many of you have used the web notebook? Actually, kind of a comparable number. That makes me happy, because the web notebook is only 2 months old. So that makes us very, very happy. So based on for a long time, all we had was the interactive terminal-based IPython, but we realized that if we have the right communications machinery, we could abstract the idea of executing Python code and communicate, if we could transfer that information and all of the events necessary to make that work well, with a suitable network transport, we could build other clients. And about 2 years ago, we discovered ZeroMQ. Brian Granger and Min Reagan Kelly, two of our core developers, went ahead and in just a few days developed the PyZMQ bindings. And based on that, we've been able to separate the terminal IPython console that you already know. That remains available, but we've been able to abstract that code out so it can run in its own process, which we call a kernel. And then different types of clients can communicate. And we currently have a terminal client, a Qt console client, a web notebook. And in addition, these kernels broadcast a lot of information so that monitoring clients can be built. So now the collection of clients that we have includes the old style IPython that I was showing before, which has for many years included support for interactive visualization. That's important to us. That means that we have to basically cooperate with the event loops of Qt, GTK, WX, TK, and the native OS X Cocoa GUI event loop. And we've done that so that interactive data visualizations with matplotlibs are possible. But now we also have this new Qt console, which was developed a little over a year and a half ago with the support of Enthought, who have been support and development from one of their developers. Which provides something that feels a lot like a console. We like the console workflow. We like typing just one command and getting results right away. When you open this by default, you could even think that it's actually a text terminal emulator. It looks like a terminal emulator, except that it's actually a Qt rich text widget capable of displaying inline graphs, of doing multi-line editing, which is impossible at a text terminal, of doing syntax highlighting, of showing graphical tooltips. So we've basically tried to build the best that we can from the workflow of a console, but with some of the rich properties that you want in a GUI toolkit. Based on this architecture, we had a meeting with Microsoft a little over a year ago, and they actually, once we explained what the communications protocol was, they developed their own client, which lives inside of Microsoft Visual Studio, and which provides an IPython console within the Visual Studio Python plugin. So I'm not a user of Visual Studio, but this is a freely downloadable plugin for Visual Studio that provides Python support. And this code this is not written in Python. This client is written in whatever Visual Studio is developed with, and they've done an absolutely spectacular job. We only had one meeting with them. We explained to them, Travis Oliphant was at that meeting, we explained to Dino and Shirok what the communications protocol was and where our Qt console code was, and we never heard from them. Next thing we know, the whole thing was released. They never had to ask us a question. They never bothered this on the list. It basically just worked based on the spec of our protocol. And finally, excuse me? Great job. Thank you. And Dino, the author of that, is sitting right there with Brian Granger. And finally, all of this was leading to something we had wanted to do for a very long time. Brian Granger and myself are both physicists. We cut our teeth in grad school using the Mathematica notebook, which some of you may know about. And we have finally, based on this architecture, last summer, Brian was able to spend a lot of time building a web interface for IPython, which uses the exact same machinery, but which lets you execute code through the web browser, talking to the same kernel, with the advantage that this web notebook, and we're going to see much more of that in a minute, this web notebook is capable of containing rich text, code cells where you execute code just like you would normally in IPython, the results of those computations, plots, and basically anything that a modern web browser is capable of displaying, you can put in there. And we'll see a little bit more about that. But finally, there's one more thing. We have the same abstractions and communications machinery that we use to control a single interactive instance is used in IPython to control actually multiple engines. And we have machinery for very high level and easy to use parallel computing, where what we have done is expose an abstraction that we call an IPython cluster, which consists of one object called the IPython controller, and n, where n can range from 1 to whatever you want it to be, n instances of a process called the IPython engine, which communicate with this controller. And all of these processes are persistent. You start them and you let them running. They could be running on a multi-core laptop, or they could be running on a supercomputer, or they could be running on an Amazon EC2 cluster that you have deployed. And then you connect to the controller with a client library that effectively proxies these engines and allows you to submit code for execution, get things going on your cluster, retrieve data for local analysis. Multiple client connections can happen at any time. So you can call a colleague in, say over the phone or over Skype, and tell them to come in and have a look at some of your data because you're puzzled. You can disconnect, go home, reconnect again to your cluster and see how things are doing. And all the while, this machinery continues working. And I will show, this is elaborate enough that an entire third of our tutorial was devoted to showing how it works. I can't do justice to the system right here. This is the second iteration of a system that we have. The first version of it was written by Min Reagan Kelly as a senior thesis here in Santa Clara, where he was an undergraduate at Santa Clara University. And last year, while Brian and myself and Evan Patterson were doing the Qt console rework of the underlying architecture, he basically, in a couple of months, Min rewrote completely the entire twisted machinery to function on top of ZeroMQ, and one of the most amazing feats of development that I've ever seen. So a very, very brief history of the project. In October 2001, I promised myself that I would take a break from my thesis, so that would be just an afternoon hack. 259 lines of code. It was a Python startup file that gave me the Mathematica prompts that I wanted and the caching of previous results. 12 years later, I'm still working on it. But at the beginning, that was just my personal hack, and I found out about two other projects, IPP and LazyPython, also written by two scientists, that gave other interactive capabilities to Python. I contacted the authors. I offered them to join forces and collaborate. They both said they had other priorities at the time, but they were very gracious and let me use their code, and so I merged these three pieces of code into what became the original IPython. In 2002, John Hunter contacted me and asked me to improve the GNU plot support that I had with better MATLAB-style syntax. And fortunately, I did have the common sense of telling him that I did have to graduate or I'd be kicked out of the country. Remember, a foreign student in the US is not always easy. And John instead took the hint that he should write a better plotting library than the other 30 that existed at the time, and thus was born Matplotlib, which is one of the cornerstones of Python's scientific computing stack. In 2004, Brian and I met after one of the SciPy conferences. We had gone to grad school together, and Min, who was a student of Brian's at the time, started working on the parallel computing code. And ever since, Brian, Min, and I have formed sort of the core of the project's development team. Between 2005 and 2009, we had sort of a slowish development period. Unfortunately, the code was very monolithic and hard to clean and work with, but some developments were made. And towards the end of this period, a very important refactoring was undertaken that allowed us, in 2010, something that worked very well, just perfect serendipity. We discovered ZeroMQ, and it landed at the perfect time after we had refactored the core, and we obtained support from Enthought to develop, on top of ZeroMQ, this communications architecture to build on top of it the Qt console. We also moved from Launchpad to Git and GitHub, and this has been fantastic for us. After us, most of the scientific computing and Python projects have also moved to GitHub, and the synergies that is giving us are extraordinary. Min, as I said, we wrote the Perl support on top of ZeroMQ, and a new developer, Thomas Cloyver, turned to be extraordinarily productive and joined us initially to do the Python 3 port, and has become also one of the key members of the team. And finally, in 2011, we released the web notebook that I'll show you more about. A very, very quick cast of characters. We have over 140 commit authors in the project at this point in the log. The people in boldface are sort of the core developers, and those in blue are simply because they're here. So if you want to talk to us, you can come later to our booth, and I'll show you later where that is. A very rapid overview of the size of the project. It has grown. As I said, it started as 259 lines of code, and we're well over 100,000, so it's not a small project anymore. It is fairly widely used. A number of scientific projects use IPython, and when I say use, I don't mean there are people who use it at these institutions, but rather there are projects built upon IPython at these places. People who use it are probably everywhere Python is used for science. But there are also, as I said earlier, non-scientific projects that use it, and it's important because I know that not all of you are scientists or engineers. This is PyCon and not SciPy. We have received support, as I mentioned before, very importantly from Enthought. From the beginning, Enthought has been a big supporter of the project. They've supported us in many ways, and we really appreciate that. Others as well, Microsoft, Sharok and Dino, who are here, did the great job that I already mentioned. We've had a little bit of federal funding, and right now we do have some reasonably steady funding from the DoD, thanks to Jose Pinco's support, and we hope to get more of that. So in summary, before I switch to the demo work, in brief, what do we try to offer for Python work? We try to offer you a much better shell, a kernel that you can embed in your own codes, and a set of clients to talk to these kernels, and high-level parallel computing tools. So this is the URL of the project. It should be easy enough to Google. And I'm going to switch perfectly on time to some demos. So this is the website for the project. And I'm going to start the demos not at the console, since most of you have seen that, but at the new web notebook, which many of you haven't. So when you start the web notebook, this is what you see. The web notebook presents you, this is running just in Google Chrome. And what it does is it presents you with an interface that's running on my local machine, but you can run it remotely. You can enable SSL and password protection if you want to put it on a publicly facing IP address. And what it does is it shows you two tabs, one with your notebooks, and I'll show you in a minute what these are, and another one with clusters. And we will come back to this towards the end of the demonstration. But first, the notebooks are documents. These are files. And so let's look first. I'm going to start with, as I said, a bit of a high wire act. We are going to look at what Twitter is saying about PyCon right now. I've been running this code through the morning, and it's been very interesting to see the evolution of the graph that results at the end. We'll see what happens. I just ran it a few minutes ago, and it wasn't very interesting. The graphs I got in the morning after Paul Graham's talk were very, very interesting. And what I should have done is run a windowed analysis of this, but I just wrote the code, so forgive me. So this is, what we have here is a text cell. I type Markdown in there, and it gets rendered as I exit the cell. And these cells are IPython cells. And whatever code you type in there is executed by IPython just as if you were at the terminal. So I'm loading the Twitter API. Now I'm running a simple query on the hashtag PyCon, and I'm going to let it ask query at most 30 pages. And I'm simply going to, let me crank up the font size just a little bit. And I'm going to simply let it filter out retweets from real tweets, and we'll see what happens. So there it ran, and it says it read 16 pages, and it found 153 tweets with the hashtag PyCon and 72 retweets. So now we filter a little bit of noise. In text like this, there's always a lot of words that are not very interesting. And with Python tools, it's very simple to compute. These are just a couple of dictionary tricks to compute, for example, some summary statistics of word frequency on the 15 most frequent words, and to build a graph of co-occurrences of those. So we're going to try to see what is the word distribution of what people are saying in the last half hour or so on Twitter about PyCon, and we will see not only the distribution of words, but also what is said in the same tweet. What kind of relationships do we see? And as I said this morning, I ran this a few times, and it changed in very interesting ways. So we use the NetworkX graph library, for which I think there's been more than one tutorial here. And then we simply print a summary. So right now, from the data set that comes out of Twitter, we have 818 unique words. Typically, the stuff at the bottom, the least frequent words, are not very interesting. They're kind of, you often see unique short URLs. These are the most frequent words from this set. And now we can build a graph and look at the structure of this graph, where what we are doing, first of all, I'm going to look at the frequency of the words. So these are the most frequent words. And typically what you see is, and I have removed PyCon, because if you leave PyCon in there, that completely dominates the figure. But in general, you see his distributions that look like this, extremely sharply peaked on a few words, and then the rest is very, very shallow. So these are the things that people are talking about right now. But if we look at what things are set together, well, it's getting better again. So these are the things that right now, whoops, what did I do? These are the things that right now people are saying together. So I don't know what Idan Gazet is, who that user is, seems to be tweeting a lot. There's a lot of great talk. Paul's name is now appearing a lot less. In the morning after his keynote, which must have been very good, I didn't see it, there was a lot. The graph was centered around that. But booth was not appearing too much. All the booth vendors were busy setting up the booth. Now all the booth vendors are busy saying, come to our booth. And you see the word come and the word booth together. And so everybody over there is busy tweeting, come to our booth. And so are we, by the way. And so this is the kind of thing that you can run in a few minutes. Now, these documents can be saved. You can put them on GitHub for version control. You can email them to a colleague. As I said, you can even turn on password protection and invite a colleague to work collaboratively with you on the same document. Think of it as Google Docs, but with a brain, with a Python brain. And everything that you have done in Python and that you've ever done in IPython works in one of these cells. Furthermore, these documents can do other things. Let me come out of. Now that you've seen sort of one actual example, I'm going to give you a bit of a tour of the things that this notebook can do. Just to reiterate, I will convince you that I'm going to remove all output, again, Highwire Act, and we're going to start completely fresh here. So if you type PWD, the kinds of things that you expect to be able to type in IPython, they work. Now, IPython, as you know, many of you probably do know, is a bit of a mix of the language and the shell. So if you define a Python variable and then you say exclamation, which goes to the shell, but you put a $sign, you actually interpolate the Python variable into the shell, so that instead of having to suffer the ignominies of looping in the shell, you can do it in a civilized language like Python and still call messages, call system commands to do the last bit of work. We activate plotting, and you already saw a little bit of this. We have very good support for matplotlib plots, so you can keep inline figures. But we can also do things like you're studying, you're trying to learn, and you see a bit of code, either from an email or from one of the tutorials, and you paste code that had the classic Python prompt. We actually filter all that for you so that you can paste input code and still execute it without having to manually remove prompts, which is very annoying. If you run a non-existent file, we actually highlight standard error so that errors are easier to read. Tracebacks, as I said before, are the same kinds of tracebacks that you get in IPython, so they're very informative and with all the details. If you run code, we actually fetch asynchronously output from the kernel. So here, I'm running a cell which is asynchronously printing. And as it prints, we actually do get the output of the kernel asynchronously, thanks to the beauties of ZeroMQ. Now here, I'm going to play a little trick with C types, which will actually segfault my kernel. So that little bit of code segfaults. And after a couple of seconds, the system detects, well, your kernel died. Obviously, the data that you had in memory, the variables are gone because that process is dead, but at least the state of your document isn't, and you can kindly restart your kernel and get back to work. And there's a separation between the document and the execution state, obviously. And we can't preserve the segfaulted kernel, but we can save your notebook. The Markdown cells can contain formatted code. So this is a cell. This is what you type in Markdown. You can even put, if you indent 4 spaces, you can put source code. You can put source code in Python. You can put source code in C. And when you get out of there, Markdown is properly rendered and highlighted and syntax highlighted. Furthermore, you can put mathematics. This for us is very important. You can put LaTeX, and we use the phenomenal MathJax library to render LaTeX both in line mode and in displayed equation mode. That may not matter to everyone, but for us it is important. Now, furthermore, we have extended, as you see here, I am returning an object whose display, this is exactly like I would get the output if I printed a computation. What we've done is we've extended the notion of Python's wrapper of objects into a protocol that allows objects to define their own representation, and their representation can be graphical, it can be PNG, it can be an SVG, it can be in LaTeX, it can be JavaScript. So we've extended the notion, and we've documented this very well, we've extended the notion of how Python objects can represent themselves. The default wrapper is meant to be a string, but you can define representations both for your own classes if you follow our protocol, and you can add a layer of representations for objects that you didn't write if you want to see other objects nicely by defining a type-based callback registry where you basically layer your own representations on top of existing objects. So this is an image object whose representation is a graphic. And the image class can also work with remote data. So in here, I'm giving it the URL of the actual Python logo from the Python website. And it works similarly to the image class. We have an SVG class. Here it's loading. I just downloaded a static copy of the Python SVG logo, and it renders it equally well. Furthermore, we have video. You can embed. This is an actual YouTube video that will play if the network is good enough. It's an actual YouTube video from a talk that I gave a while ago. So you can imagine, I'm not going to play it for you, but you can imagine all we have done is simply create an object called YouTube video. You pass it the YouTube hash of the video, and then it will embed it in the page. So you can imagine writing tutorials, you can imagine creating documentation where you have a video, the person pauses it, then they work through a problem if you want to screencast with built-in exercises. Now, currently, this is using YouTube, which means it's using Flash or the embedded YouTube player. But now browsers are getting to the point where they support embedded video. And so here, what we have is a local file. I'm opening a file called animation.m4v, which is a local file. I'm reading the data, I'm encoding it in base64. And if I run this cell, now Chrome, actually the video support in Chrome is pretty good. It loads a local video. So you don't have to put your things on YouTube. It's a little tricky to get it to work. We haven't figured out all the encoding details. So this one works. Sometimes it's failed. But we know that browser video, A, is getting better, B, we don't know too much about it, so I'm sure that somebody would tell us exactly what's going on. But the point is, at least this shows that it's possible, and this is likely only to get better. You can even, where am I? Let me keep going. So this is actually, you can embed, as I said, anything that a web browser can. So this is actually an embedded copy of the Wikipedia mobile page, and we can search in Wikipedia. So this is the Wikipedia search for Python. So you can imagine putting other content in your live documents that refer to other things. As long as they're in the web and an iframe will support it, you can put them in there. Finally, the mathematics support that I mentioned earlier. Before, we showed how to type mathematics into Markdown cells. That's when you are typing. But the representation protocol that we have extends to math. So this is an object whose representation is LaTeX and provides a mathematical view. And so based on that, we have built extensions for the SymPy symbolic computing system so that you can run all of the SymPy algebraic computations that SymPy is capable of doing and get your results in properly formatted mathematics, because since SymPy knows already how to produce LaTeX versions of anything that it computes, it's completely, once this is in place, it's simply a matter of basically layering and telling SymPy, whenever you print a repr, give us the LaTeX form, because once we have the LaTeX form, we can render arbitrary LaTeX. JS Math is really, really good. So we didn't write the LaTeX parser. We simply use, MathJax, not JS Math. We're using MathJax. One of the things that you often do when you're learning something is load external codes. So for example, we use Matplotlib a lot, but this would apply to anything else. When people learn Matplotlib, they often have to go to the gallery because they don't quite know what they're going to do. And so they browse the gallery, they find an example that does what they want, that looks close to what they want, and then they try to execute it. And the Matplotlib gallery and the scikit-learn package has a similar gallery, the scikit-image package has a similar gallery. These are galleries of examples with a script, the figure, and a link to the source code. And typically you would download it, go run it, etc., etc. So if you find an example and you find the source code link, you can either drag and drop or copy and paste. I'm going to remove that so that you see that I'm actually doing it fresh. We have a function called loadpy, which can take a local path or a remote URL, and you simply give it the URL, it loads, it fetches the script, loads it into the next cell, and then you execute it, and you have your example. So it's very easy to basically grab existing examples from anywhere on the internet, put them in, tweak them, because now I can go and I can tweak them. I can go and change this to be, I don't know, and it immediately re-executes. Well, that was the label down here. It doesn't show very well. But anyway, you can, this is now the code that you execute. You start changing it, and it becomes, so the transition from seeing an example online to executing it yourself is absolutely minimal. And I still have a few minutes, so I think I'm going to be, okay. Because finally, I want to show you guys another part of the notebook, which is, first of all, this, which is the SymPy example that I was telling you about. So we provide an extension called SymPy printing, which basically layers our representation protocol on top of SymPy's existing LaTeX machinery, and it lets you produce this kind of environment where anytime that you compute anything with SymPy, then the result is automatically rendered correctly as you computed in proper symbolic, with proper symbolic expressions. And SymPy actually can work together with NumPy so that you can combine numerical examples and symbolic work. So these are illustrative examples. I'm not going to go through them in detail, but where you can combine SymPy's symbolic Taylor series expansions, for example, with NumPy and Matplotlib to do numerical work. And all of this, once this is loaded, then this behaves very much like a classic computer algebra system, but through the web with nice representations. You can then grab these files and say, give me a print view. And the print view is simply a static HTML view of it that your browser is then capable of either saving as a static HTML file if you want to put it up on your website or somewhere, or which your browser is capable of printing into a PDF. If you want to print it on paper or email it to a colleague who doesn't have the system, you can produce a static view of this. And we are busy building converters so that this, for example, exports into Sphinx and similar systems so that you have more control. The underlying format of these files is a JSON, a very well-structured JSON format that is very amenable both to version control and to machine manipulation. We've gone to great lengths to try to make that format easy to work with. Let me find my way in my tabs again. And so finally, so that I have a few minutes for questions, I am going to show you the other part of the interface, which is the clusters. As I said before, I'm going to unzoom a bit so you see the entire width. These are configurations that I have for different clusters. These are my different configuration profiles for IPython. Some of these could be configured to run on my systems at work. One of these could be configured to run on EC2 with all the necessary authentication machinery. And here, IPython lets me start or stop any cluster. So I can say, for example, stop my default cluster or start it again. And once this cluster is running, I can go and run code that executes things in parallel. So this is a quick example that I'm going to do. There is no time really to go through all the details, but the point is to show you that fairly complex things are relatively straightforward to do. In this case, what we do is we grab an object called the client, which is a proxy into the running cluster, and then we make a view. Views are basically, well, views into these engines that have different execution semantics. You can have a direct view, which is effectively a multiplexer that sends code to be executed on all your engines, or a load balance view to which you submit tasks and which then schedules these tasks. But there are fairly elaborate execution policies available. And what this demonstration does is using the same library that I'd used at the beginning to construct the graph, the beautiful NetworkX library from Los Alamos National Lab, it builds a directed graph of dependencies, the kind of thing that a build system would compute. Make or any build systems under the hood is computing a dependency graph. So in this case, we're by hand building a random graph. So we're building a random graph of dependencies, which is simply a bunch of tasks, and these are the dependencies between them. Who knows what produced this? It doesn't matter. The point is to illustrate that you can schedule all of this bundle in one shot and tell the IPython cluster, do all these things and do them in the right order. These are their dependencies. I got these dependencies from somewhere else. In this case, we made them randomly. But these are my jobs, and they have this very complicated list of interconnected dependencies. In this case, we're going to define the jobs or simply wait a random amount of time so that this completes, because I am actually going to run it live, so I don't want it to take too much time. And then all we do is we create a dictionary of jobs, where in this case every job is just wait a random amount of time. But then we say schedule the results, and since we have the graph, all we have to do is sort them in topological order, and when we assign, this is the line that actually does the code execution. When we say whoops, don't do that, do this. When we actually do the code execution, we simply say, run this job after its dependencies, where its dependencies are the predecessors in the sorted graph. So with 2 lines of code, we're scheduling this with the correct topological order. And now, if I say wait, as you see, it tells me the kernel is busy. I'm actually waiting for the completion of these jobs. But if you notice, the first execution returned immediately. It returned immediately because it's asynchronous. I could keep working while my cluster is computing. Once I say I actually need the answers, I can wait on it, and then I get my data. And we're going to validate that things ran correctly. This is basically a visual proof of the theorem. What I'm doing, now I need to make it smaller so that you guys can see the whole thing. This is a visual proof that the execution was correct in the following manner. The directed graph, the thick part of the line is the arrowhead, and we're running time towards the right. So basically, as long as all the arrowheads lean to the right, everything ran in the right order. There are no, if we ever see an arrowhead pointed in any way towards the left, that would mean that something ran before its dependencies were met. And the fact that this is not a mathematical proof, but it's a visual illustration that the dependency order was correctly met. So in a couple of lines of code, you can schedule fairly elaborate things and have them run. And as I said, the cluster continues to run. Where is my little, here it is. I have to unzoom a bit. The cluster continues to run. I can see, close the others so that we don't have as many tabs open. client.it. What did I call my client? RC. These are the IDs of the client. It means it has 4 engines because that's exactly what we started here. Once we stop the cluster, then it won't be able to connect. So this shows you how basically our philosophy has been to integrate together around the tools in IPython, something that lets you go from interactive, one person toying with an idea. At the notebook, you're playing with some data, you're playing with a problem. In our case, which is scientific research, you start saying, well, this may have legs, I want to collaborate with a colleague. So you can share these tools, you can work with them with a colleague, you can scale to production work in a cluster, you can put this on Amazon and scale this to large-scale production. And at some point, hopefully you got some results that you want to show to others, so you can produce HTML, PDF, or publishable results from this, and finally use them to teach, because at the end of those, hopefully you use those results to teach to someone. And we think that this is also a good tool for teaching. So it's sort of what we call the cradle to the grave life cycle of ideas, from exploring a new idea that may or may not pan out to completely presenting it in its finished form. And we're trying to build tools to make that possible in a fairly seamless way. So I think I do have a few minutes. I was asked to keep about 5 minutes for questions. So I am going to now close shop here, but we do have a booth. So please, we're right by the left, on the way into the exhibitor hall. You make a left and we're at the booth. We have a booth there where we can demo this. We'll be happy to talk to you guys. We will have a sprint. Some of us will stay during the sprint days, and we're going to meet with Olivier Grisel, who's one of the lead developers of the Scikit-Learn project, to try to basically make it very easy to put the beautiful tools that the machine learning Scikit-Learn project is developing, combined with the IPython parallel tools, to make it easier to run large-scale data analysis and machine learning projects in large parallel environments. So if some of you are interested in those topics, come on over to the sprints, or come and meet us and we'll chat with you. While the next speaker sets up, I have about 3 minutes for a few questions.
We have a couple moments for questions. Thank you, Fernando. That was a great talk.
Yes.
You spoke about collaborating with folks and sending something to be shared with someone else. Can you talk a little bit more about how you would go about doing that?
So yes, so the question, I'll repeat the question for the recording. The question was, how does the collaboration mechanism work? The current implementation is fairly limited. Right now, what you can do is you can invite obviously you can share these files on GitHub or email them, whichever way you want, or you can invite someone to basically share your session. What we don't have is any kind of real-time synchronization. So we have a tutorial on how to enable password protection and SSL encryption on the traffic. And once you enable that, you can give that password to a colleague, give them the URL where the notebook is running, and then they can connect and they will see the same execution session. The only catch is that you have to save the file and the other person has to hit reload. So the way we do it basically is you're on the phone or on Skype, you save, the other person reloads, and you keep talking, and you basically have to hand off the typing to one another because there's no visual indication of that. But it simply hasn't been done. Keep in mind, this notebook was released right before Christmas, so just a little over 2 months ago. We would love to collaborate with people who are good at web type development to make that mechanism better.
Can you talk about what is possible right now with Sphinx and in the future in terms of getting code to
So the question is about Sphinx exporting. We have not even in the main code base, I put it up just on a gist. We have a very, very simple restructured text exporter. The document format is extremely simple. The JSON is very easy to traverse. You don't even have to traverse it yourself. You just run an iterator that we provide. And so improving that exporter is very easy. And what we would like to have is basically easily produce a Sphinx compatible version of a notebook so that you can loop it into your document production cycle. The work to do that is literally a few hours worth. If nobody helps us with it, we'll just finish it one of these afternoons, but we've been kind of busy. This is like 4 conferences in 3 weeks, so we just haven't had the time to do it. You're welcome to swing by our booth and I'll show you exactly what the code is. It's easy, fun code to write. Let me know when to stop once the next speaker is.
How feasible is it to use IPython as a replacement shell? Like if I just want to run it instead of Bash or Windows shell?
Ask Mark Wiebe, one of the core NumPy developers. Apparently he does. And because on Windows, the default terminal isn't very good, he uses the Qt console as his default shell on Windows. I personally don't, but I know people who do. Many people do. I don't, to be honest. And on Windows especially, it's very, very popular. And more so now that we have the Qt console, which makes a really nice environment.
Thank you.
Hi, thanks for the talk. Has there been any thought given to debugging in the interactive notebook and
Yes.
thoughts about that?
So that's one thing that I failed to mention, that I failed to show. Right now in the notebook, you can type Qt console, and it will open a console that is plugged into, oh, I don't have the screen anymore. I'm sorry, I forgot to show this. If you type Qt console, you do get a console which is plugged into the current running kernel. So you can use that to use %debug and interactive debugging. Or you can even connect from a terminal with a text console to a running kernel. I failed to show that, I'm sorry. But we also plan on making it possible directly through the web widget. It just hasn't been done. It's one last 0MQ socket to wire, and a little widget needs to be written. So it's a little bit of work. It's not an afternoon, but it is in the cards and just needs to be done. I think that's it.
Thank you again, Fernando.
Thanks for your attention.